Okay, so first, let me start with the motivation. So as the title suggested, I want to bring reactive programming available on the bare metal. Why do I want to do that? You have these different kinds of sensor devices, these embedded devices with various sensors. They produce data, and you want to do something with the data on the device itself. But of course, these devices have only limited memory capacity, have only limited processing capabilities. Something is going wrong.
The screen sharing stopped.
For the remote audience, I have just showed the motivation slide without any content, and it's this one. The memory capacity has limited processing power. Usually the memory capacity is expressed in kilobytes. The processing power is expressed in megahertz. So if you want to put a regular reactive programming language on there, I mean, you really need to squeeze out everything you can in order to write something cool on one of these devices. And the main motivation of the reactive programming language that gives me more precise control over the memory allocation and consumption behavior. And there's also a secondary motivation, like I want more control over the execution time, but that won't be that. But if you're interested in that, come talk to me in the lunch break or coffee break or whatever. So first, I wanted to see how existing reactive programming languages look like. And I divided them in two different categories. On the one hand, we have function-based implementations, and on the other hand, we have graph-based implementations. Now, function-based implementations, these are usually implemented on top of Haskell or Agda or other functional languages. And examples of these are like from, Yampa, SFRP, Dunai. And the main idea of their implementation is, well, yeah, it's written in a functional language like Haskell. So the main way how they make reactive programs over there is essentially by composing functions. Graph-based implementations, on the other hand, are implemented in other languages, like, for example, father time is implemented in Scheme or Racket. RE Scala is, well, you guessed it, it's implemented in Scala, and so on. So these are graph-based implementations, and the main distinction here is that reactive programs are no longer a function that has to be applied. It's now a graph, and at runtime, we're actually just going to propagate values through that graph from top to bottom, from the sources to the sinks. So let's look at these implementations in detail. So here's like a snippet of the sequential composition operator of Yampa. So you have one signal function or one reactive program, you have another one, and you want to click them together so that the sinks of the first one are connected to the sinks of the sources of the second one. And this is the implementation that does that. And what this implementation tells me is that at runtime, it needs to do two separate things. So the stuff in blue is the code that's responsible for propagating values. But while that is happening, there is also the code in yellow, and that's the one that constantly has to re-glue the reactive program back together. That's needed, for example, if like the first signal function does something stateful, and then the composed signal function also needs to do something stateful. And they support this by letting a signal function actually produce a modified version of itself. And in this way, they also implement switching behaviors and a lot of more complicated stuff. But the issue of this code is that if you actually start to run a simple reactive programming language like this one, which just adds 1 to a number, and you start to look at the memory consumption behavior, you see that it constantly needs to allocate and deallocate memory because it constantly has to apply these functions, create new chunks, and so on. So what I say is that this is chunks galore. Like every time you do something in Yampa, it needs to apply a function, which means allocating more memory, and at the end it has to deallocate the memory that it produced from the previous run of that reactive program. Now, I'm lying a little bit on this slide because this is not actually the graph of running that code, but hopefully, depending on how much time I have left at the end of the presentation, I can go into that. So the real graph is even worse than that one. So that's the important part. So graph-based languages, on the other hand, they need expensive data structures. Now, why do I do these air quotes? Because on a desktop computer, on a laptop, on a mobile phone, it's not that expensive to have a priority queue. On a small scale embedded device, on the other hand, yeah, you don't want to constantly work with these kinds of data structures. So in order to propagate changes through this graph, what usually happens, there are different approaches out there, but like the standard approach for me, is that you assign a height to every node in the graph. And once you do that, you can compute the height of a different signal by just taking the maximum of the signals or the nodes that it depends on and adding 1 to it. And you do that over and over again, such that at runtime, you start with the ones with the lowest height, and then you start looking for the ones with the highest height. And that way, you can avoid glitches. So like inconsistencies in the way how you schedule these signal updates. But the problem here is that you also have continuous memory allocation, because you constantly have to make use of the priority queue. You have to enqueue data on it, so like which node it is and which height it is. And there are, of course, ways to like constrain that in one way or another. But like the really bad thing here is that it's actually expensive to reconfigure the graph. So, for example, if you replace this node is plus with another node, which introduces a lot of additional dependencies, we have to update dependencies of everything that's underneath it. And that's going to be expensive in the priority queue as well, because then all the heights have to be reassigned. We have to update the heap and whatnot. And that's definitely something we don't want on an embedded device. Now, something that's shared between both function-based applications and graph-based applications is that they make use of lifting. And what that means is that we can actually just provide in the case of Yampa, we can just provide any Haskell function we want. It may take 300 years to compute. It might allocate 50 terabytes of memory. And the reactive language is going to be like, okay, I'm fine with it. But of course, the reactive language will no longer be reactive if we would use that kind of function over there. And the same issue we also observe in graph-based implementations. So here's also an example in RE Scala. And there we can just write any Scala code we want. And of course, that's something we want to avoid. So in a way, these languages, these embedded reactive programming languages, they lose control whenever they ask the host language, hey, can you please evaluate this function for me? Because then, yeah, monsters be there. So I will now present mine or our own little reactive programming language called Hi, which is designed from graph-based principles. So that gives me full control over the way how we implement it. I'm not relying on host language, so I don't have lifting, but for the rest, it's your regular reactive programming language. So it has turn-based propagation, so there aren't any glitches there. And here's a quick example of a program in Hi. It's a reactor. So reactor is the main computational unit of Hi, named average. It has 3 inputs or sources, X, Y, and Z, and then we compute the average of X, Y, and Z, and the graph here represents the same program over there. And the idea here is that this reactor, it's just a description. If we actually wanted to react on something, we have to deploy it. So here we deploy average on, for example, 3 temperature sensors. And of course, if we can then connect it to a fan, so if the temperature is too high, we turn on the fan and so on. So Hi, the main identifying feature of Hi, and that's also where the name comes from, is that it has support for higher order reactive programming languages. I assume that most people don't know Dutch, but like Hi is a Dutch word for shark, and that explains the logo. So recently, I was interested in trying to write a formalism of Hi. So that's what I'm going to present today. But first, quick something else. I actually made a formalization in summer, before summer, because I already presented the formalization of Hi at a different workshop, like FGB, which was a workshop at eCoop. So here I presented a formalization of reactive programming. So if a program is a set of reactor definitions, and the reactor definitions is a set of nodes. And what I then did is that I defined the operational semantics of graph-based reactive programming languages. And that's, if you're interested in that, it's that paper. But today I'm going to talk about the other paper, because I made a second formalization. And the name of that formalization is REMUS. And the idea of REMUS or REMUS is that it like specifies really well how you can put reactive programming languages on the bare metal. So REMUS is a formalization of a virtual machine, so not really the bare metal, But that's because I didn't want to look at an actual processor specification and figure out the real assembly. And I didn't want to do that, so it's like abstract, like really generic, but like I think it's quite cool because you can reason about it in the terms of the reactive program itself. So what I did is I specified the syntax just as before, but now it looks different. Now the reactive program is a set of reactor definitions. With these reactor definitions, now I just have like a sequence of instructions of a sequence of commands. So it's no longer a true graph. So in general, like the way how you would make use of an actual implementation of REBLS is you have your high program, you parse it into a reactor graph, and then that reactor graph you can compile into a REBLS program together with all the other reactors that it consists of. You take all these REBLS programs, you flash them together with the virtual machine on an embedded device, and you have your functional functioning reactive program on bare metal for like an embedded device. So I could now present the formalization in detail, but let's not do that. I don't want to bother you all with lots of complicated results of LaTeX expressions. I don't want to do that. So instead, I'm just going to present like the basic insights that we gained from making this formalization. So here is another reactive program. It's called circle area, or a reactor called circle area, and it computes the area of a circle. So here's the graph, and here is the bytecode of that reactor. So the main identifying feature of REBLS is the fact that it has two different kinds of instruction sequences. There are deployment instruction sequences, which are like the constructor as in class, as in object-oriented programming. And then there is like the reactor instructions, and those specify how data should flow through the reactive program. So imagine that somewhere in the reactive program we have a reactor called main, and that reactor makes use of circle area. So what's going to happen is that the source value is going to be inserted somewhere to remember the input of that deployment, and then we're going to execute the commands. It's the first time, so we're going to execute the deployment command first, which is going to allocate some memory somewhere to remember the sources for the multiplication. Then we have the supply command, or the supply instruction. That is just going to look at this value over here, or this operand over there, and it's going to send that value to that deployment. So in this case, the deployment of the multiplication. So we're going to do that 3 times, and then we're going to react. And what react is going to do essentially is at the end, is going to make sure that its output contains the right value. Like, it's not rocket science, I know. And then we have another instruction called consume, and that allows this deployment to consume a value from the sinks of another deployment. And then we have a sync instruction as well, and that just stores that value over here as the outputs of the deployment itself. So the main idea here is that these instructions, they refer to each other, and like we assign for each instruction, we allocate some memory where it can store its output. And then of course at the end, the computation in main resumes. And the good news here is that we avoid the constant memory allocation that's usually found in function-based implementations of reactive programming languages. Because here we just constantly make use of this memory region, even later when there's like a new turn happening, you've already allocated it, so we can just simply reuse it. Of course, if we deploy the same reactor more times, we're also going to have multiple memory regions for each deployment. So like we can't simply reuse them if we reuse the same reactor in the program. So in short, like this piece of code, this describes a possible ordering in the way how data flows from these different nodes and reactors and deployments as in the original graph-based formalization. And we do this essentially by just doing a compile time topological sort of each reactor individually, and that way we don't need that expensive priority queue as before. Now, a more complicated example is this one. That's a reactor that computes the area of a rounded rectangle, and the idea here is that it actually makes use of our circle area from before. So once again, here's like its bytecode. I removed some parts because they're not necessary for the explanation. So those are the inputs again, those are the instructions. We have already executed some of them. So we're going to supply the radius, which is stored over here, over here. It's going to be stored over there. Then we're going to react. And what that is going to do is like save a pointer to where we were when we were executing this part. And then the commands or the instructions of the deployment of the circle area are going to be executed. And then after those have been executed, the computation resumes over there by consuming it. And then in the end, we store a sink just as before. And this is good news because we have reentrancy. We don't need to create a copy of the reactor every time we need it. But the bad news is we have an update stack because we have to keep track of where all these pointers were. And yeah, stack, so memory allocation, so bad news. Maybe not, it's not as bad as I presented right now. Because if you don't have recursion in the structure of the dependency graph, then you can, at compile time, also determine the size of that stack. And checking for recursion is, in this variant of I, very easy, because you just have to make sure that there are no forward references to other reactors, and that you don't use the reactor itself in its own body. We don't have a wide combinator, as in, for example, lambda calculus. If you have recursion, yeah, there might be some issues there, but like I just say, it's future work. I'm gonna worry about that later. Then finally, higher order programming in I is also supported. So here's a program. It's going to define a signal called shape area, and just assume for now that sometimes the value of that signal is going to be circle area, and sometimes it's going to be triangle area. And we're also going to assume that right now we cannot determine which one it is or which reactors it can be statically. So if we compile this program again, we get something like this. And there are two new instructions here. The first one is make poly. And make poly is going to create something that I call a branching point. So it's going to create an identifier of a branching point. And it's the first one we created, so its index is 0. And now imagine that our 8, so the 8 reaction instruction has specified that we have to deploy or make use of the circle area in this turn. So what that is going to do is it's going to allocate that deployment, but it's also going to store it somewhere in which I call the toggle environment, which is going to remember in this branching point over here, I've encountered a reactor called circle area, and its deployment identifier is 4. So for the rest, nothing really changes. We have, once again, supply to supply the right values to that deployment. But of course, this time it doesn't point to something in the deployment instructions. This time it points to something in the reaction instructions, because it's a runtime decision on which reactor has to be deployed during the turn. So for the rest, everything functions exactly the same. We have the supply, we have the reactor, we have the consume, and we have the sink, and in that way we compute the area of the shape that we wanted. Now, if later there's another turn, and now we don't want to deploy the circle area reactor again, we now want to deploy the triangle area reactor, we're going to create a new deployment of that reactor, and we're also going to store it in the toggle environment. So this shows that it's like less expensive to reconfigure the dependency graph. We don't have to update priorities, we just have to make sure that we deploy the reactor, and at React, we jump to the right one. Often we say that we toggle between these different deployments that we've created before. But of course, benchmarks work in progress. So I don't have numbers that show that this is faster, but my gut feeling tells me it's going to be faster than going through the entire graph and updating everything again. It's like no benchmarks, sorry. So a final note, there is a weird similarity between higher order programming and conditionals. So here are two examples. So this is the code from before. We have an if the time is even, shape area is going to be circle area, otherwise it's going to be triangle area. And this one does exactly the same, but without the higher order deployment over there of shape area. And what's actually going to happen in both scenarios, like I said, at runtime, it's constantly going to decide, am I going to send data to the deployment of the circle area, or am I going to send data to the triangle area? But the difference here is that this is implicit because we don't specify where it can toggle to. That can come, for example, also from a source. It doesn't have to be specified in the body of the reactor itself. While in this case, of course, it's explicit. I really specify which two options there are. It's either the circle area or either the triangle area. This code over here is almost doing exactly the same thing as well, but doesn't do the toggling. So it's going to send data to both the circle area deployment and the triangle area deployment, and it's only at the end when both of them are computed that it's going to decide on whether it needs a C or a D, whether it needs the area of the circle or the area of the triangle. But in this case, all programs produce the same values. So like a quick glance on the formalism. Okay, everyone with me? Okay, let's zoom in on one rule, which is the alloc mono rule, which is going to specify what happens if the virtual machine needs to process or like execute alloc mono command or an alloc mono instruction. In the paper I used command, but I prefer to use instruction actually. So what that's going to do is going to create a new deployment. So it's going to remember the name, and then it's going to store it in a set of deployments that exist. I don't have enough time to go over the configuration itself. If you're interested, look at the paper. And then two other rules, alloc poly new and alloc poly existing. There are two rules needed for specifying the semantics of the alloc poly instruction. And the idea here is that we're first going to see for this branching point in the program and this reactor that we want to deploy, if it doesn't exist already in the toggle environment, yeah, we're going to create a new one and going to store it as well. If it already exists, we're just going to reuse the memory that we've allocated in a previous turn and just move on. So in this case, of course, we're not modifying the toggle environment. We're only modifying it if you're allocating a new reactor. So some final thoughts. This is the question that I have myself. And if you have any ideas, let me know. Are the two formalisms equivalent? So I presented interpreter vision at FTFGP at eCoop this year, and I've now presented you the virtual machine vision. So the idea is, the question I have is, are both formalisms describing exactly the same thing? Are both, if a program is put in that one, this program is put in that one, are they always going to produce the same values? I think the answer is yes. I haven't proven it. Something else, implementation. So the formalism, it's available online. I've implemented in PLT Redux. You can just go on our GitLab, clone the repository and play around with it if you want to. Link is also in the paper. But something else that a student of mine is doing right now, she's trying to implement the formalism for real, not in PLT Redux, but in Rust. And currently, I can't show you because the battery of this thing is dead. But like, there is an actual implementation of Remus running on this thing, but not right now because the battery. So yeah, that's in short everything I wanted to talk about. So if there are any questions, let me know.
So, a question, a comment?
That's silence.
Okay, so I have a question. Okay, I have a question. Okay, so you gave some formalism, and I have formalism. So does formalism help the, let's say, the implementation of this kind of thing? Yeah, this kind of formalism. So do you think that this kind of formalism helps the, let's say, towards implementation of bare metal machine?
The main reason why I made the formalization is because it's easier to present than, hey, look at my Scala or Scheme implementation of the language, which consists of 30,000 lines of code. Like the formalism, I know the font size is a bit small, but it fits on a slide. I can't do that with an actual implementation. So that's one reason why I did the whole formalization. The other reason is because I'm actually really interested in knowing if the formalism I presented at FTFGP and the one I presented today, if they're describing the same thing. In order to, because I have an actual implementation of the graph-based approach, I have now an actual implementation of the virtual machine. But of course, I mean, it's the same program, so you want to be absolutely damn sure that it's the same program on both types of systems, whether or not you do it the graph-based way or whether or not you do it with these instructions. But like, I'm working on that right now. But like, that's also the reason why I made this second formalization.
So that, I think that you may have some kind of theorems about memory violation things. So this program can run on some fixed size of memory or some other kind of things.
Yeah. So this formalization, like I don't prove or show anything useful like for actual programs. Like I don't have like an analysis that you put in a reactive program and it then tells you, you need this amount of memory. If you want that kind of processing speed, like events processed per second, you need that kind of processor, and so on. So I'm not doing that, but the formalization, I think, helps in better understanding where exactly you need to allocate memory, which is different from other reactive programming languages and other formalizations, because they essentially just assume that a garbage collector exists. They're not focused on an actual implementation for these kinds of devices. And by making this formalization, I now know exactly where memory has to be allocated. And yeah, it's when you deploy something. But of course, that's in the case of my language, because I don't allow lifting. If you would allow lifting, you would also have to analyze the embedded program. So if you would do some kind of analysis for RE-scala or father time, or for Dunai and so on, I mean, you would also have to analyze the original the functions from the host language. And I'm glossing over them because I don't support them. I'm only focused on the memory allocation of the reactive program itself, because that's the only thing I have.
Thank you. Okay, so any other questions or comments?
I have a question.
Okay.
Hi, thank you for the talk, and it's good to see you again after FTFJP. I have two questions. One is, are you planning on doing sort of more proof on your formalism, or like mechanized proof maybe? And the second question is, apologies if I missed it, but is there any sort of discussion of sort of concurrency in the bytecode that you were showing us today? I might have just missed it if there was, or it might not be.
First question, the answer is ongoing work. I'm trying to do it, but like I'm not an expert in mechanized proofs, so I'm like looking into that. I did try making a proof on pen and paper, and I think it's going the right direction. It's not finished yet, but like I think I think I have a way to show it. Like, yeah, not a mechanized proof, unfortunately. So that's something that I have to look into after, maybe. The second question, is there any concurrency involved? And the answer is no, because I don't think a lot of embedded devices have like good support for concurrency. So like it's a really basic, it's all single threaded, but the graph-based formalization was also single threaded in a way. So like it wasn't the main goal to tackle concurrency in this paper. But could be interesting to look into.
It wasn't, thank you. It was really interesting.
Any more question? No? Okay, thank you very much. Thanks for